Hi there. So, my name's Leon. I'm here to just talk about geospatial data and how I use it during my day-to-day and in my charity work. So this seminar is more data and data analysis focused than data science, focusing on the geospatial data. What I'm going to do is give a little introduction, pretty high level, to geospatial data and GIS tangentially. Then talk a little bit about my company, Viridian Logic, and how it uses analysis of geospatial data to figure out where to map habitats to reduce flooding and combat climate change. And then finally look at map action, which employs data in humanitarian emergencies. So, a little bit about me. I graduated in 2015 with a PhD in astronomy. Whilst I was finishing up my PhD, I started working in environmental risk consultancy. A little later on, in the wake of the Brexit vote, I started my own company with my current business partner. And the next year, from the line manager that I had in that risk consultancy, I started volunteering for Map Action. So let's start off by talking about geospatial data. So this is just going to be a high-level look at data rather than tools. The map that you see in front of you is just a travel map of surface coloured by where they're from and where they're travelling to. It's just a fun map visualization, giving you the idea of what sort of questions you can start asking with geospatial data. So on geospatial data itself, geospatial data just refers to data that can be put on a map. So where locations or areas are just extra properties of the map, of the data that you have, and these spatial properties are called spatial elements. Geospatial data can also have multiple non-spatial components, so much like a regular database, but they would specifically have a spatial element to them. Geographical Information Systems, or GIS shorthand, allows one to manipulate that data for presentation and analyses strictly within spatial sphere. So on geospatial data, geospatial data are generally classified into these two categories. So they are vector data and raster data, vector data being spatial elements which are described by points or collections of points. So if you imagine lots of points in a row, that will make a line. When that line closes in on itself, that forms a polygon. So you can imagine vector data as being a database with one dedicated spatial field, also referred to as a geometry field, to basically tie in the properties that you want with areas on a map or on a globe. Raster data are basically images where each pixel has a projected size and orientation on the globe. Pixel values then tell you something about that location, such as land height or topography, volume of rainfall, or temperature, or fraction of vegetative cover, and so on. So let's have a look at some examples of vector data. So I've got a few maps here. Let's go from left to right. Leftmost is a route map made up of line geometries and additional point geometries labeled as landmarks. You can see the train representing the station, the little medical briefcase representing some sort of medical center, and the tall buildings representing something with tall buildings. The map is as complex or as simple as you'd like it to be. Going to the upper left image is a hexagonal binned heat map or cartogram. And this one's just of tweet frequencies for some hit Twitter hashtag in Europe, where you can just vaguely see that the points are distributed around the shape of Europe, where those tweets occurred. On the lower left image is a choropleth map. Countries are color-coded by the Human Development Index. So dark colors imply higher Human Development Index than the lighter shades. And The upper right map is of 1.2 billion taxi journeys, starting and or ending in Lower Manhattan, helps you show likely congestion spots or traffic hotspots in doing it this way. But that shows you sort of the power of GIS in terms of being able to visualize what's going on the ground. And then finally, in the lower right, you might be familiar with an epidemiological issue at the moment. So this is a map of COVID hotspots, visualizing strains and likely transmission paths, as well as the hotspots themselves. And so this sort of helps us understand the transmission paths and how COVID reached various parts of the world. Now looking at raster data. Raster data, like I said, is just basically image data transposed onto the ground. So you can see that a lot of these look like they're derived from satellite data, because generally satellite data will be transmitted as raster information. So on the upper left is just vegetative cover by type using satellite spectra. The lower left is what a land height map or topography map looks like. The middle upper is what you're probably more familiar with in terms of topography, and that's basically the slope, steepness, and orientation with respect to what the height map is doing. Lower right is a precipitation map, again using satellite spectra to determine clouds or like cloud bursting clouds. And upper right is a surface wetness map, again from satellite spectra. And so those two sort of data categories are with vector data and raster data. So vector data generally categorizes data into having certain properties, so areas or lines. So lines would be different types of roads, or areas would be different districts or postcodes and so on and so forth. And raster data would be more continuous data. So like I showed you with the rainfall data or land height. This isn't necessarily exclusive though. So vector data can communicate topography as well, such as ISO lines. So heights, so you might have seen the Northern Survey map. This would be less accurate than raster down to what's going on the ground, but it gives you a general feeling for what's going on. Raster data can also categorize areas, but it's limited to a single digit index where some external lookup is needed. So geospatial data have certain properties which make them compatible with one another. So units, which I guess is kind of basic, but relating to the spatial aspect of the data. So coordinates are generally expressed as a pair of numbers, and they're either expressed as global degrees, so an easting and a northing, or in a local metric frame, again, easting and northing. And in terms of a raster, that would be the same way, but the pixels are of some angular metrics or size as well. And those can be converted between angular and metric sizes so long as the data contains within the metadata a projected coordinate system. So allows conversion from one set of units to another. So the reason that you'd have different metrics is because globally you'd be cleverer to store your data in terms of a spherical geometry, just so that you have one set of coordinate systems to play around with. And then when you deep dive in, you probably want a more local thing, so you want to change it to the meters. The reason for this being so is because the Earth is not a perfect sphere. So, and because it's also on tectonic plates. So the exact geometries and alignments of the surface of the Earth are more matched by individual projected coordinate systems mapped to the surface of the Earth. I guess those are the real big gotchas with geospatial data, but this is just a high level look. Anyway, from our brief introduction to geospatial data, let me now talk about my company, Viridian Logic. So Viridian Logic was started with the idea that floods are a problem, this is a picture of New Orleans sunsets. This is in 2015 when it was flooded. The floods of 2015, estimated by the Environment Agency, cost the UK somewhere in the region of £1.5 billion. So it's something which we'd like to help tackle. The traditional way of dealing with floods is where it floods, you build infrastructure, so walls along rivers and spillways to capture excess water and let it pass by the area which would otherwise get flooded. But this sort of means that areas downstream will also then receive that water and then possibly get flooded. So the trick that Viridian logic wants to play is to, instead of trying to trap the water when it arrives, slow the arrival of that water to those locations. And to do that, it's basically involves planting further upstream within the landscape so that the water doesn't travel quite as fast into the riverways, becoming a problem. And this is just returns green infrastructure. So there are two main approaches of doing this, which exist in industry today, apart from Viridian logic. One is hydrologic modeling, which is basically calculating the flows of water over landscapes, but this doesn't tell you where in the landscape those flows are best intercepted. The other is GIS, which I've just introduced to you, which is using multiple data layers to determine where the best opportunities for planting exist. Now, the best opportunities for planting exist somewhat independently of where flows go. So this doesn't necessarily tell you where the best places to plant to reduce flooding are. So Viridian logic just simply takes the step of combining those two approaches to determine where are the best places to plant things to slow flooding. Now, during the course of making the company, I've also open sourced some software. This is an old module now since it's Python 2, but this was made in conjunction with, to support basically the Natural Capital Project. Natural Capital Project is a collaboration between WWF, Stanford University and the University of Minnesota in terms of analysing the landscape to better the environment. So I wrote this preprocessor and made it open source back to them so that they could use it as well. What it basically does is calculate water flows over landscapes and determining how much a pixel is being loaded upon from all the flows upstream and what opportunities it has downstream before it reaches a river to lose or shed any flood load or pollutant load. A few other tricks which are in that library are just separately IDing riverbanks. So as you know where flows are entering the river, this is because if you put an intervention on one side of a river, it won't slow water going in on the other side of the river. And another piece of work is just basically matching up two different data sets. So like I said, you can convert, so this is actually a demonstration of conversion between a vector data set and a raster data set, as I mentioned before. I've taken a vector data set, which is this blue line, which is just a river center line. And I have my, what is called the digital terrain model, my land height model, which is the grays underneath. And you can see that they don't quite line up. So this module takes those two data sets and takes that blue river line and tries to push it into matching the topography of the land, which you can see in the red on the right-hand side there. So in action, here's a case study of this village called Fulani. And this is what we output from that. So going in, we have things which are the land use. So you can see there are forests, there's lots of built up areas, there are roads, and you can generally see the topography and the rivers flowing north. So in terms of the data layers, we take this land use, we look at peak monthly rainfall, soil texture, and indeed geology to then determine the solution. The machinery behind this, the solution is basically showing a ranked So using statistical ranking, it determines where the best places are to plant in terms of how deep the shade of colour is. The different colours which will refer to the solutions are green, blue, and you might be able to see a trace of orange around the place, which is grass. So that refers to, the green refers to woodland, blue refers to wetlands, the orange refers to grasslands. Grasslands tend to hug the rivers, so being on the riverbanks, they just tie them up together better. The wetlands basically are very good at holding onto water, so delaying the flow of water down the landscape. Trees perform a similar function, but they're also good at holding pollutants as well. So yeah, the deeper shades mean just a higher priority than the lighter shades. And so this covers the whole landscape, and what I'm showing on the screen is probably the top 20% of solutions. Now, an issue with this is that because I've done it with statistical ranking, I can tell you where the best places to plant are, but I can't tell you mechanically how much that will reduce flooding by. So in terms of a slightly more data sciencey angle, what I'd like to do is be able to take a calibration point from somewhere in a river and tie that down to what happens in a default setting when there's no vegetation being taken place. And then tying the scores generated by hydrologists, which are ranks, to this cost-benefit curve. So that would be effectively a reduction in the peak flood heights of that river monitoring point, let's say. And we'd expect that as you plant more, you'd reduce the flood peak more, but it would be a decreasing return on investment, ROI. So the amount of benefits for the amount of cost would reduce. The reason that this would be useful is just to show that I'd be able to say if there is a target flood reduction needed, I'd be able to say that from doing the best thing in the first place, which is what the algorithm already produces. So again, you can generate an uncertainty and a fit just by taking out cross-validation and taking in multiple calibration points to be able to determine, right, what is the general cost benefit and how sure am I of that cost benefit. So that's sort of a basic data science model. Now, the dream is to actually really overhaul the whole mechanism. So much of the work of the Natural Capital Project has been great, and it's been allowed us to come up with this way of solving the problems caused by climate change by also producing solutions which combat climate change. There's some things in there which are just academic guesswork. So the Natural Capital Project, WWF, Stanford, University of Minnesota, provide weightings for the factors going in. And as you can see from the table, they basically are about a quarter or about a half, which is something which looks a lot like guesswork. Now, this is academic guesswork, but it is still guesswork, and that might be the best that could happen in the 2000s. But now we're getting into a regime of computing where we can just solve this. So the way to do this is, if you look at this slightly nasty looking equation, this is just what the flow accumulation effectively looks at, weighting up the different factors and adding them together over the total flow to then figure out over the flow path to figure out where the optimal balance points are. But what we can actually do is, if we simply reform that equation, since it's basically a sum of multiple different and unique data sets, we can separate out the actual calculation and just do that calculation over multiple machines. That way the weights only attach to the data sets that they're affected by. So most of these data sets are just properties of the land. The way that the dream data science AI would work is to then leverage precipitation, which is not a property of the land, and it also changes quite a lot. So you'd take it, well, we would take in multiple precipitation maps or precipitation events, and then we'd want to tie them to river monitoring points within the landscape. And by tying those together, we can then basically hammer down what those weights should be to optimally match what the scores are coming out from hydrologists. Hydrologists is the name of the tool, sorry. Optimally balance what comes out of our data with actual physical data that would give us proper quantification of what our tool is determining and how much flows are being reduced by. And this also leads to other things. If we take a historical look on, say, land use as well as hammering down on precipitation, we can start to figure out things like what's determining the whole flow of the river. So you know that rivers will flow whether it's been raining or not, and that depends on the underground aquifer. If we can determine a whole history of precipitation, then we can sort of determine what's going on with the aquifer and how much that's contributing to a river height, and therefore start thinking about what's called groundwater flooding, as well as just surface water flooding. And that's basically the state of affairs for Viridian logic and its data science ideas. Anyway, segueing ungracefully into what map action does. So map action, as you might be able to tell from the name, makes maps. Anyway, a bit more accurately, during a rapid onset humanitarian crisis, such as a flood or a hurricane or earthquake, it's important for aid workers, responders, to know what areas are affected or what areas are most affected, where vulnerable populations already exist, and where relevant infrastructure and services, such as healthcare facilities, are located, so those people in need can get to those facilities. The way that we break this down in map action is by having sort of 3 levels of map product. The base map, the baseline, and the situational map. So the base map is fairly straightforward. It's your Google Maps, your OpenStreet Maps, your local government data that already exists in a map format. The reason that this is useful is simply because the aid workers can come from anywhere in the world, and they will just need a quick understanding of what's on the ground already. The baseline demands a little bit more work. So this is some work which we've started automating in map action. Since we know where we fetch statistics from for a set of countries, we can start automating those things for regions which experience regular hurricanes, such as the Caribbean or in Pacific Islands. So we find those statistics and we what we call geocode them, that is, turn them into spatial data so that they can be mapped and they can be compared with other spatial data to get an idea of what the situation was on the ground before the disaster hit. And then we get into the real meat of what map action do, which is the situational maps. So this takes in the rapidly evolving ground situation, which requires good data management to be able to then piece together different pieces of data or spatial data and identify trends or problems or gaps, and ultimately deliver aid to those people who need it, rather than letting it go to waste into the wrong place and so on and so forth. So as an example of some map actions work, we've been out and deployed to Nicaragua and Honduras for Hurricane Iota and Eta. So this is a map, one of the maps that we produced, which is just tracing the hurricane track and looking at precipitation, where was flooded, where was hit, and where was likely to be damaged. Also, you can see that we've color-coded the hurricane along its path, which is to show, right, the extent of the damage would be maximum at where the hurricane is red, and then the hurricane sort of dissipates as it travels across the land. So we've got an idea of where was damaged as a result of the hurricane more likely, or was it because of the underlying infrastructure being poorer? And as we know that there were multiple hurricanes this year, the reason that they're called Eta and Iota is because the naming convention for tropical storms is generally given from first names from A to Z. There were so many tropical storms this year that they had to go into the Greek alphabet to name them. So these are just, again, hurricane tracks and then coloured by categorization, again, to give an indication of how fiercely these places were being hit. In terms of more data analytics type stuff, we had a look at sort of the number and fraction or proportion of homes that were damaged during Hurricane Eta and Iota, to just sort of get an idea of, right, where is the aid needed, and what if people are bringing shelter kits like UNICEF or Oxfam, where they should they be delivering, who is most in need, can we and how should they be distributed, and how they should coordinate that distribution effort. In terms of something a little bit more data sciencey, a few years ago there was the Hurricane Maria, and this is Dominica, the islands in the Caribbean. And so we've got a set of two maps. The map on the left is showing how much water is being supplied relative to the number of days. And that then allowed us to combine that with, well, how many people live there, and then how much water should they need as a humanitarian standard, which is 15 litres a day. So using that information, we can then say how many days of water are left in these locations, and therefore how much water needs to be delivered to these places. And as you can see, it's quite a desperate picture. A lot of places only have 1 day of potable, drinkable water. Anyway, I hope that's been a useful introduction into geodata and some of its applications. I'm happy to take questions. Please look up my company on viridianlogic.com or the charity I volunteer for, mapaction.org. Thank you very much.